We discussed in the last lecture some of the examples which of the disconnected species and connected species. So we discussed that Q, the set of all rational numbers is a disconnected topological space, and we use this result of finding a continuous function taking values in 0 and 1. And then we discuss this example of capital X which is connected, and later on we discuss this important result, which is that if I have a topological space which is disconnected and it has a separation, and if A is a connected subspace of X, then A will fall in either U1 or it will fall in U2. So A is a subset of U1 or A is a subset of U2. So this is a very important result we will use today also. And then we discussed that if I have a collection of subspaces which has a common point in the intersection, then its union is connected. So later on, yeah. So later on, I discussed this example that if X is disconnected, then it has basically two connected components, U1 and U2. So this is basically what we discussed in the last lecture. Let us start today lecture. So today I will start with another important basic result which we can apply on examples. So let us start with that. So this is a theorem that let X be a topological space and A is a connected subspace of X. So if I take another subset of X, so whenever I consider a subspace of a topological space, that means B is a subset of X, and on B we have a topology which is coming from topology on X as a subspace, as a subset. So that is the subspace topology, such that so B is a subset of X which satisfies the condition that B is between A and A closure. So then B is connected. In particular, A closure is also connected. So what this result says that is, if I know a subset A of X is connected in the subspace topology, and I have the set B which is containing this set A, and it is a subset of the closure of that set, the closure of A. So B contains all the points of A, and it is a subset of A closure. So what is A closure? A closure is a union all the limit points. So basically B in B, which we have some more points other than A which are limit points of A. So that is exactly meaning of B is in between A and A closure. So then we want to prove such a set B is always connected. So in particular, since B is a set between A and A closure, I can in particular take B equal to A closure. So since from this theorem which will follow, B is connected, this set is also connected. So let us try to prove this result. So what we know is that we are given a subset of X such that that set is contains all points of B and it is subset of A closure. So this is given. What I want to prove, we want to prove that B is connected topological space in the subspace topology. So B is connected, that we want to prove. We will assume that B is not connected and we will get a contradiction. So that will prove that B is connected set. So assume that B is disconnected. So B is disconnected means we know that every disconnected topological space has a separation U1 comma U2. So since B is connected, we have therefore there exists a separation U1 comma U2 of B. So now we know that what is meaning of the separation. So separation means U1 and U2 are non-empty disjoint open sets such that is union of U1 and U2. Right? And since U1 and U2 are disjoint sets and its union is B in the subspace topology, so U1 and U2 are open in the subspace topology on B. So we know that whenever separation exists, U1 and U2 are both open as well as closed sets. So that we discuss after the definition of separation of a topological space, that if U1 and U2 are separation of a topological space, then U1 is open as well as closed. Same way, U2 is also open as well as closed set. So now we have a separation, and then we will use this result which we have proved, that if I have a connected subset of a disconnected space, so I have a separation of a topological space and in which I have a connected subspace, then A will be either in U1 or it will be in U2. A is contained in U1 or U2. So same way here I have a subset of B and A is a connected set, right? So since A is subset of B, which is connected, A is connected, and B is equal to U1 union U2. Therefore, so this is lemma, I think, yeah. So therefore, the lemma which we proved using a lemma we proved, we will get. So what we will get is A will be either subset of U1 or A will be either subset of U2. We get A is a subset of U1 or A is a subset of U2. So we have two choices. A is either subset of U1 or A is subset of U2. So again, without loss of generality, we assume that A is a subset of the first separating set. Right. A is subset of U2 is second case in which we can give the similar argument as A is subset of U1. So now if A is a subset of U1 and we know that U1, U2 is a separation, so therefore U1 and U2 are both open sets as well as U1, U2 both are closed sets. So now what we will get is to go from A to B, I have to take the closure, right? So so now what I will get is taking closure on the both sides. So I will get A subset of U1. So A closure is subset of U1 closure, but U1 closure is U1. Why? Because U1 is closed. U1, U2 is a separation. So any set which gives us a separation, that set is always open as well as closed, because U1, U2 are disjoint. So its complement of open set is closed. So finally what we got is A closure is a subset of U1, and what is B? B is a set in between A and A closure. So therefore B, which is a subset of A closure, which is subset of U1. So finally we will get B is a subset of U1. And what is U1, U2? U1, U2 is a sets whose union is B. U1, U2 are non-empty disjoint sets. Its union is B and B is subset of U1. So these both things will give us that since B is equal to U1 union U2 and B is subset of U1. If these both things are true, what we will get is U2 is a non-empty. U2 is an empty set, right? Because if my set B is contained in one set whose union with other set is that set, same set, then that means the second set is empty set. But this is not possible because U1 union U2 is B. It is a separation of B. So this is a contradiction. What is the contradiction? That U1 U2 is a separation. So U1 and U2 both should be non-empty sets. So this is a contradiction to the fact that U2 is non-empty set. So this contradiction coming because we have assumed that B is disconnected space, right? So therefore B is a connected space. So this will prove this result, and this result is very important for the examples. So let us go back to the statement again. So this result says that if I have a topological space X, and in which if I know that some set is connected, then if I take any set in between in between the connected set A and its closure, all those sets B are always connected. So in other words, if I know some set A is connected, and in that set if I add as many limit points I want, then by adding those limit points, the new set is also connected, right? And in particular, if I add all the limit points, then I will get A closure, and that will give this last condition that A closure is also last conclusion that in particular we get a closure is also connected. So before I take any example of this type of application of this theorem, let me define some terminology which is known as locally connected space. So a topological space is called locally connected. So we have seen connected topological space. Now this definition is regarding locally connected topological spaces. If the property is satisfied, the property is that X for each. So let me call this topological space some notation that X is given topological space which is locally connected if for each element X in X and any neighborhood U containing X we can always find a neighborhood, another neighborhood say W of X such that X belongs to W which is a subset or equal to V. So this is the property of locally connected space. Pardon? Right, you're right. This is U. Thank you. So this is a typo. It is U. Correct. So this is the definition. Let us see one simple example. So if I take X is a standard with the standard topology, X equal to R with the standard topology. So let us see this this set. So consider. Okay, so question is that is X locally connected?
Yes, sir. I think yes.
Yes. So how we will show this? So we will start with sorry. We have to let us give some simple idea. So what we will do? I will take any point on the real line. Let us say X. So now suppose I have some open set. Neighborhood means it is an open set which contains X. So let us say this is my open set. I can take union of two intervals also. That is a open set containing say X. So for example, I can take X minus 1, X plus 1, or even I can take X plus 2 also here. Then this is X plus 3, and let us say this is X plus 3.5, whatever we take. So this X is contained in the open set X minus 1, 2x plus 2 union, let us say x plus 3 to x plus 3.5. So this is open neighborhood, whatever I'm taking. Actually we have to take general neighborhood, but just I am showing you. If this is a particular neighborhood, then can I find a neighborhood which contains x and it is subset of this particular open set? So for that, the basic idea is I can take a kind of half interval or something like that. So I can take x minus, let us say, half, and on this side I am taking x plus 1. So x is contained in x minus half to x plus 1, which is a subset of this set, which is open. So what idea we are using here, in fact you can take here specifically x equal to 1 also for a more special interval example. So actually we need to show for every arbitrary open set which contains x, I can find uh, another open set which is contained here. So the idea in this solution is basically we are finding, what we are finding is this is a basic open set which is connected, right? So whatever open set you give me which contains given point x, I can always find basic open set that is a open interval which is contained in this set and it contains x. So this is the idea. So therefore R is locally connected. So in more detail, what argument we use here is that if I have a topological space X which has a basis in which each basis element is connected, then X is locally connected space. So so for example, for giving more clear idea, what it says is if x equal to r, let us see that example again. And if I take any real number and if x is contained in the open set, then since x is in the open set, there exists a basis element b in b such that x belongs to b, which is subset of u. And here what is b? B is basically open interval. So this is connected. So therefore the condition of this locally compact space is satisfied. So therefore R is connected. So even the same argument works in R2 also, because if I have any open set containing a point of R2, I can always find an open disk which is contained in that open set, and the open disk in R2 is connected subset of R2. So let us see some other non-trivial example. So here we will see some example of a connected space which is not locally connected. So let us consider set. So we are taking a sets in R2 So if I take x comma y, where x is 0 and minus 1 less than equal to y less than equal to 1. So this is my set A, which is subset of R2, and I'm considering another set B, which is xy such that 0 less than x less than or equal to 1, and I'm considering the y coordinate using the function sine 1 upon x. So let us try to draw the graph of these elements. So we take R2. So what is our first set? Our first set is that all the points xy such that x is 0. X is 0 means I have a y-axis and my y is between minus 1 and 1. So all points on y-axis which are between minus 1 and 1. So let us say this is my minus 1 and this is my point 1. So this vertical line segment is basically the set A, all the points on that. And what is B? B is x comma y such that x is in the open close interval 0 1 and whose y coordinate is sine 1 by x. So basically we are considering the graph of this function sine 1 upon x when x is between 0 and less than equal to 1. So 0 point is already contained in the set A, so except that we will start with x equal to 1. So at x equal to 1, sine 1 upon 1 will come here, and then so this is my line y equal to 1. So this sine 1 upon x graph, it will touch here when I will have point 2 upon pi, and then it will come back to x-axis and it will touch at x-axis at the point 1 upon pi. So later on you can check all these things, and then it will go below up to minus 1. Then again it will come here, and slowly these intervals will become low, right? So I have not drawn the graph properly, but you can see in the book it is given very nicely. So this is our these are all the points of B basically. So let us consider the set X, which is subset of R2, which is union of these two sets A union B, and note that B is basically the graph of the function, right? So the function sine 1 upon x. So basically B is nothing but f of 0 comma close interval 1, where the function f is defined as f of x equal to, so let us write f of t equal to t comma sine 1 upon t. So the graph of this function is basically y equal to sine 1 upon x, and that they are all the points where x is between 0 and in the interval open close interval 0 to 1. So B is image of this function, and this function is continuous. F is continuous, It is continuous because we are not taking 0 in the domain. So it is continuous, and therefore f of the continuous image of connected space is connected, therefore this set is connected. And what is this set? This is a B. So why f of 0 comma 1 is connected? Because open close interval 0 1 is a connected subset of subspace of R. So therefore image of that continuous image of that connected space is connected, that is B. So B is connected, and what is the relation between B and X is that if I take this graph, and if I consider if I consider all limit points, then all these points will essentially converge to this particular point on the y-axis, and that is element of A, right? So every element of A can be considered as a limit of elements of B which are converging to that horizontally. So all the points of A will belongs to the closure of points of B. So observe that A is actually a subset of B closure. So therefore what we get is uh, A union B is X, and X is A union B, right? And B is also subset of B closure, A is also subset of B closure, so A union B is subset of B closure. So essentially an X contains B, so therefore X is exactly B closure. And what we know is B is connected. So now we can apply this result that if I have any set between the set and its closure, then that set is also connected. So therefore X is also connected subspace of R2. So B is also connected subspace of R2. X is also connected subspace of R2. So basically what we used is we use this result here. Therefore we have taken the closure, and this B is different than what B we are taking. So the set B which we are taking in the example is actually A, and its closure we are taking, so B is A closure, and that is basically X. So here notation there is some confusion, but what we are using is essentially this result we are using. So X is connected, and the important thing to note is that X is not, however, X is not locally connected. Subspace of R2. because as we have discussed in the case of R, in every whatever open set I take, I can find a interval inside that which is contained in the set. So if I consider X to be locally connected, then I should be able to find around in every open set I should be able to find a connected basic open set which is contained in that set. So note that if I take any point in X, let us say this is my point in X. So X belongs to A, therefore X belongs to capital X. So if I take any open set which contains X in R2, so that will be the intersection of that will contain basic open set. So therefore it contains a disk around X, and if you see the intersection of this open set, let us say U, which is open in R2, so U is open disk in R2. If I take U intersection A, that will be opening in the subspace topology on A. So what will be the points it will contain? It will contain all these points, all the points in this line, all the points here, all points here, this point, and this point. And now we can see that this disk cannot contain if, what I have drawn is all these points U intersection A, and this U intersection will not contain any disk, any open disk in R2 which around X, which contains the point X. So there we can see from the graph itself, because it contains kind of line segments. So there are 5 line segments which we can see there. Of course there are other line segments because in the we have drawn the graph up to this point only, but it is going forward, right? So U intersection A contains infinitely many line segments of this form, but this union of all these line segment will never contain a disk, right? There cannot be any disk around X which is entirely contained in this set. So therefore this set is this set X, capital X, is not locally compact. I think I have done some mistake here. I should write here X because we are checking X is locally compact, right? Not A is locally compact. So I've taken point X in capital A, which is a subset of X. Right? So therefore finally we can write that it is not locally compact because we can see from the diagram that for a point which we have chosen in the diagram, which is element of the set X, which is particular in A, has a neighborhood U intersection X, which contains X, but there is no open disk B in R2 around X. Around X means it contains X. And it is a subset of U open set in X. So because the intersection of U and X is kind of line segments, so it is not containing any part of any disk. It contains only line segments. So this is one of the example that we have a connected space, but it is not locally connected. Okay, so maybe I will stop today here because you have a quiz after this.